just equations. So pause aside, please. Pull up your equation sheet and make sure that these are there, because these may show up in your test. So we start from here on the left, and then we go one at a time so that everybody gets a fair chance. All right, so let me ask this. Remind me your name again, sir, please. Aiden. Aiden, remind us, just name it. Just please answer everybody. Answer just the question that I ask, so that I get to ask other people with other questions. I want to have enough questions. This is relatively big class. So remind us just the topic that we went over last time.
The torsion.
Torsion, and that's it. Torsion. You said Aiden, right?
Yeah.
Aiden.
O'Neill.
The first letter of family name?
O'Neill.
O. The first letter. Follow the instruction, please. Is it O?
Yeah.
Aiden O. Yes. Yeah. If I call your name, please just help me with this format: the first name and then the first letter of your family name, so that I can quickly find us. As time moves, I become faster. So, your name, sir, please?
Tyler.
Tyler. I thought that today you have the competition. It's not that today?
Yes.
Was it today?
No, we're doing a presentation today at 12 an hour.
Oh, okay.
Sorry,
I see.
I was finishing setting up.
All right. Yes, that is torsion, Aiden. Give you your point. Secondly, for torsion, for every loading case, we should always be prepared for the dominant stress type. So do not give me the equation, just name it. What is the dominant stress type for torsion?
Torsional shear.
Torsional shear, that is correct. Torsional shear. Then, Dylan, I want you to give me the equation for shear stress due to torsion.
Is it tau equals V over A?
First of all, you should not ask me, answer me. It is.
Tau equals V over A.
Tau equals
V over A.
shear due to torsion. The one that you said was for axial load. Your name, sir? Sir, your name?
Nathan.
Nathan, good present for you, but next time you might have class starts at 10:15. Nathan, family name?
Second?
Family name?
Schaffer.
Yes.
Tau equals TR over J.
Very good. Tau equals TR over J. Dylan, point. All right, your name, please?
Nick.
Nick.
Nicholas.
Nick, first letter family name.
R.
Nick R, thank you. Yes, I found you. Nick, in that equation, tau equals TR over J, what is the long name for the parameter J? And then Jesus, you please prepare for the meaning of it. Geometrical meaning of it.
Like the equation for J?
Just the name for it, the long name for it.
Oh, second polar moment of inertia.
Area, actually. Second, polar moment of area.
Of area?
Yes.
Oh, okay.
In case I said that, I apologize, because there is inertia also, but that's for area.
Okay.
Second, polar moment of area instead of inertia. So Nick, your point. So Jesus, what does it measure? What's the geometrical meaning of J?
It measures the circumference of the shaft for torsion or
No, that I would say 3 meter. 3 meter would measure that.
okay. The twist. It measures how much twist is getting performed on it. The torque. Shear.
It somehow shows up in those equations, but it measures something else. All right, it's okay. Anybody else? Raise your hand if you want to. May I go to policy? We already. Actually, I'm not sure. I have to be fair. was open question, you almost raised at the same time, at the same time, lack of sleep. So I'll give you also a chance. It's open.
Resistance to torsion.
What did you want to say? Be honest. What did you want to
Measure
say?
of resistance to torsion.
Correct. Yeah, please write it down. Jesus, Wasi, and Nick R, right?
Yeah.
Okay. Each get a point. All right, Kiro. Now, Kiro and Jacob, we had two specific cross-sectional geometries. One was solid circle, the other one was hollow circle or tubular geometry. So each one of you give me the J equation for one of them.
So,
For solid,
the first solid one, it would be, J is equal to 1/2 pi R naught to the fourth.
it's in fact our outer, in that particular case, our outer, yes. Point to Kiro. And then Jacob, please give me that for tubular.
The hollow one is J equals 1/2 pi parentheses R outer to the 4 minus R inner to the 4.
Very good. Basically, you're subtracting the J of the outer and the inner. All right. I know your name. You help me.
Justin.
Justin, yes, Manner. Justin, what's the unit for J? Was something perhaps you've seen the first time. If you look at the equation, you can tell that way too.
Is it radiant?
Radians. And we said a measure of resistance to torsion. It's not angular deflection. Look at the different examples we did. Josiah is just ready for it.
I don't think I wrote down the units.
Josiah, go for it.
Meters to the fourth.
Meters to the fourth. All right. Then, next person, please remind your name.
Oh, graded?
Braden, and then first letter. Please
A.
follow this format. A. Braden A. Yes, I found you. Braden, give me please the angular deformation or deflection equation. And the next person, you please prepare for shear strain equation.
Would that be phi equals T times the length over J times G?
Very good indeed. Josiah, what's the name of the parameter G?
Modulus of rigidity.
Or shear modulus or shear stiffness, right?
Okay.
Yes, all those things. Josiah, name, a point, and then, I'm sorry, next person, your name? Sir, are you following? Your name? Nathan Smith. Nathan, you give me please the shear strain equation. Shear strain. Right, this is relatively big class. When I was teaching this, let's say, with 15 students, it was almost half the work. It was easier for everybody to follow. So please help each other out. It's a lot of work for me. But if you pay more attention, it just makes it easier so that I can do more work for you guys. Are you ready? Yes?
No, I'm sorry.
All right, go for it.
Y equals R O over L? I'm not sure what.
You're looking at the right equation.
No, it's not right.
I'll give you a point for that, but it was not correct pronunciation of the words. I'll give you a point, but I want you to fix it, please.
The shear strain, shear stress, and then shear modulus.
You said everything.
I'm trying to remember what some of these are called.
So say the equation now, I'll help you.
Y equals T divided by 6 G.
No, that's not. Yeah.
Is it?
It is. And you emphasize it too, it
Yes,
is.
yeah, it is.
Emphasis,
R
it is
times-
rather than isn't.
R times the angle twist divided by L. Or
Very
phi.
good. So what's the name of the parameter on the left? Do you want to trick me?
Phi.
The left, on the left.
Oh, gamma.
Gamma. Jesus. Tyler, write it down. Gamma equals R P over F.
Yes. To measure the angle twist, and you can use that to shear strain. It's R times phi, or the angle twist.
Justin, remind me, you answered 2 questions today, right?
Yes.
All right. Then I move on to, just like you answered already, I think I know your name. In the interest of time, help me.
It's Cole.
Yes.
Yeah.
Help me with this. So we said in practice we can figure out whether this is made of ductile material or brittle. Suppose I twist it and then it fades. You look at the fade surface, and by looking at that, you can comment whether this is this or that. What is that?
It would be brittle or ductile would be completely straight, basically, and then brittle would be 45 degree.
Very good. Is it only this or what about this?
It could be both.
Very good. It could be either. All the points. And then let me see what else we have. True. When we twist it, where do you expect the maximum shear stress to occur on the cross section?
We'd expect the most amount of stress to occur. Sorry, stuttering.
Take your time.
Well, we'd expect the maximum amount of stress to occur near the center of the kind of where it
So suppose I torque it like this, I look at this cross section, right? It's circular, it's solid. Where is it maximum on that circle? Is it interior, is it outermost, where is it?
You'd expect the most amount of it to occur on the outer radius.
Outer radius. And what is the value right in the center?
Yeah, at the center, the value would be
0. Yes, and the outermost is maximum. True. Yes, true point. Alright, and then we want to, well, see, let's do this example together. Let's start with you, I'll give you time. And then maybe Tyler also, I may get to ask you also a question on this. And also, Mochler, Evan, you might be also part of this. So let's go over this together. Again, we're still in the realm of torsion, and all those applications that you said previously would apply. So this is a shaft connected to possibly to another shaft through these pulleys. So this could occur in conveyor, for instance. So belts are connected on these two and then to another shaft. And the belts are measuring these two torques. But the problem is asking for shear stresses on the two segments, on the two shafts. All right. Mossy is asking for shear stress and it's about torsion, then we should immediately write down the equation for that. So please give me that.
Torsion for shear. TR over J.
When you say equation, two sides, the left.
Shear tau equals.
Yes.
CR.
So tau equals TR over J is the equation as you said. And what is the J in this case? A solid circle. What's the J for this?
Yeah, so
What's the J equation for this?
1 over 2 pi r to the 4th.
Very good. So we have to repeat this each time, basically do this for one of the sections. So this is for A. This is BC. All right, what's your point? So Tyler, I want you to help me with numbers now. Let's do torque calculation later, but you gave me R value for AB. Let's do in parallel. Give me the radius for AB, please. It's basically test of vision. Can you see that from
No,
now?
I can barely see the board right now. So, so 3046.
What's the radius?
Radius, oh, sorry, that would be 15 and 23.
And it's a milli, right? What's milli?
In millimeters,
What's milli? 10 to?
third,
10 to?
negative 3.
Negative 10. All right, Tyler, point. Yes, Kiro.
Is that 46 or is that 40 millimeters?
This is 46 millimeters. I get these figures from textbook, and then some of them are not very good resolution.
Bless you. Yeah.
All right, Evan, we want to figure out the torques on the two shafts. So yes, at these 2 points, the torques are given by one the torque in here, or the torque on the shaft in here. Right? We did a similar problem in here. You remember how we figured out the torques in these segments, having known these two? You remember or not? All right. So in the homework we said you're supposed to know this, but let me review this. So we said this. We want to figure out the torque in here. All right. So there are two torques externally applied. You have to consider the effect of each one at a time. So if you apply TA, the torque at point A, would that cause any deformation in this AB or not?
Can you repeat the question?
If you apply the load here, will it cause deformation in AB?
Yeah.
All right. If you apply load here, would you think it would cause any deformation in AB? No. That's why you said TAB is just TA. See that? All right. Now let's talk about this. Again, we want to look at the effects of these two loads on the segment. That would be the torque on this. All right. If I apply this torque, would it cause any deformation in BC? All right. If I apply this load here, would it cause any deformation here? That's why we superposed the two. We subtracted the two just because the two are in reverse direction. You see that? All right, so now look at this, so this is the subtraction. If you are in the same direction, you just add them, otherwise you subtract them. Look at this. We want to look for the TAB, calculate this and this. Let's start with TAB. Look at only this segment and enumerate the effects of this and this on this segment. If you apply TA, will it deform AB? All right. If you apply TB, will it deform AB? No, it will be just TA. All right. What about BC?
It'd be both of them added.
Very good. Add it. In the same direction, add them. Remember, for the homework, those should be added. All right. Then give me values, please. TAB would be?
Which one?
TAB.
TA would be 300.
TBC?
700.
Very good. All right, I want everybody, calculate these two and get 2 points, and then bring it to me, let me see it. Let's just quick do that all in megapascal. And at the point before I forget. And then remember that it will be next, is it, what's your name, ma'am? Yes,
Olivia Walker. Olivia Walker.
Olivia. All right, so next will be you. But when you're ready, just bring it to me, and welcome to class. Make sure, again, you want them in megapascal, you have to divide by mega. Mega, remember, is 10 to 6. What you get out of your calculator already is in Pascal. You divide that by 10 to 6. Have a question? If you want to show me the value, just bring it to me. Question?
Did you put I over 2 for this?
Yeah, thank you, yes. I'll give you a point for your precision gate. Very good. Those are 2 points to you. Rise faster. Yes.
Yeah, I understand.
Overall, I'm just saying.
That would be like intended.
First one, yes, two. Read this calculation, seems to be something new. I thought yes. 2 points to you. What is it there? I take it. Yes, 2 points to you. Read this calculation. Where is this calculation? Oh, you have to redo it, and then this was incorrect. Redo that. Where you put all the 2 points. Shuffle. This number is 23. Oh, yes. That's good. I don't. Craig. These ones, I mean, you should ask me that. Gray. Gray, that's the first letter.
You got it. Hey.
The conversion only one, right? You divide with it.
All the time.
Then if you divide by 10%, then this goes a bit like this, right?
Oh.
This yes. And that's 1%.
Oh, I see.
You do that.
I always want to know this. Because it goes line by line.
This is correct. This is incorrect. Read this. And it's very weird. Didn't, yes. The first one.
Okay. Third over pi second divided by pi second times 23 to 10 to the negative third times to the fourth.
Hero one, grab the second one. Yes, good. Correct. Then sharp.
Calculate.
That's good. I need just a letter from somebody. Okay? If you just send me that, doesn't every policy, it's not you, it's for everyone. That is correct, that's correct. I see. No worries, that's what we do in this, but we fix all the issues. You get better, right? Yeah, that's correct. Two is sufficient. Manner. Yes.
I just found my bed.
This one is off. Let's see what it is. Read what says this is it. That's correct. Yeah. It's just. Just the value of practice will help us. Just by that, we want to necessary should be parentheses. So this is not correct. You're not bringing a calculator. Alright, looks good. Now this is good. Now this is good. Rate it R. A, sorry, A. Oh, yeah. Yes. One last call. One last call. 1 second, bring it, bring it. Is this yours or his? This is yours or his? How come he has it? You see the second? Yeah. So this is not. Yeah, you're just glad.
I can tell you what it's gonna be, but there's things that doesn't.
The first.
Most of them, I think you're gonna see it. Never gonna get it. I know Lexi has one too.
Yeah, the first there.
Well, I think they trace
Yeah, that's correct. Johnson or Hudson?
It's more bad, and I don't know that way. But
Johnson, your family name?
they didn't thought of it, so I have no idea.
Are you following this? This is 23? I got that exactly. Yeah, this makes sense. All right, guys, let's finish it. That's correct. The first one. One of the first. Oh, but it's so now it's good. I saw you first already, right? Yeah.
Zach, we already talked about.
All right, guys.
Wednesday, March
56.
4th, 11:30, 1:30.
59, 36.63. So guys, you see that as my, if you judge to yourself now, you see that some of you did really fast, accurate, like Josiah, and some had some small issues there. So what we're doing, our goal is to really resolve those precision issues. Right? So as engineers, you're expected to be precise. We're practicing that. I mean, this just 2 calculations that took us about 10 minutes. So we have to speed up. We have to speed up. We want to get better. If you continue working like this, let's say slow for now, if you keep this trend, we're not going to be able to cover much. That's not good for you. Then you make me change my approach, and it will not be good for you. All right? So to be able to continue better pace, and still I really have this approach, let you all do this, and learn at most, then you have to do faster. You have to get to know your calculator better by doing this practice. Some of you had some issues, and then when you fixed it, you got back to me, you found, oh, this was the issue, this was the issue. So as you do this more and more, you develop a more detail-oriented eye. So practice just gets it better. All right, so we did that. Any questions, guys? All right, good. So we want to do this. This is the last example. But I want to cover something in here. Kinematics. Of gears. So it's a closed, rather closed, guys, please, guys. It's a closed topic, like what we learned in high school. I'll give you more time. Let me put more. Is it Nathan? Sir, what was your name?
Aiden.
Aiden. I'll give you more time. Let me fill that up and then take pictures so that you have everything. So as we learned in high school, we learned trigonometry, right? Trigonometry was a closed topic. We learned sine, cosine, tangent, cotangent, and then here, even in college, we're repeating that. There's nothing more to that. So we call it simply closed topic. So gears is almost the same thing. Yes, research is being done, but not on kinematics of it. So what does that mean? So I believe we have Harvey Davidson in Flint, if you're into motor bikes. So why they're expensive? Why others are less expensive? So a lot of research goes into different components. In terms of gears, what they do is this. They say, we want to develop gears that when you gear up or down, smooth. There's relatively, let's say, almost no noise there. And also for repeated usage, it should really have that quality. So stability matters there. So really developing gears that has good profile, good quality, performance on the teeth, and it should be almost noiseless. The research is being done, but not in terms of size of it. So that's closed topic that I want to go over here. So I don't know which course you would go over this specifically, like trigonometry. It's not one particular course. So I give all that information that you need, and you're welcome to use it in the other courses also. Okay? So write it down and use it in other places. So it all starts from here. Suppose two gears are in contact, A and B, RA, RB, the radius of each is given. Suppose on this we have torque A, we measure the deformation A, and the angular velocity omega, so this is called omega. angular velocity. It's basically d phi over dt. You do not need this parameter in this course, but in dynamics you do. So I covered here, it's just a simple thing, you use it there too. And the question is this, I switch the color here. We want to see what are these three parameters on the right one, if these two are in contact. Geometrically, these have to be equal, these have to be opposite, not equal necessarily. So I want to solve for TB, BB, and omega B. All right, I always derive these from scratch, easy to do. So start from here. Imagine the teeth that are in contact is the angular phi A, and this is angular deflection or deformation phi B. I reason that this arc length at contact is the same whether you view it from the left or the right here. And from math, I know that radius times phi gives me that length. So it gives me this relationship that phi b over phi a is inversely proportional to the radii. Derivative, take derivative. Therefore, this is the same as omega b omega a. If you know how fast one of them goes, you know how fast the other one goes. Given that you know the dimensions of the two gears. So this ratio of gears simply is referred to as gear ratio. So this is called gear ratio. Which one is input, which one is output? Radio ratio. That's the meaning of it. All right, if now I look at the common force at the teeth, I can say the torque over radius is the common force. We know the torque is radius times distance times force. So I can write this equation for the two. Therefore, this time, the torques are inversely proportional. Actually proportional to radii. So these are the two equations that we need. So to put this in perspective, let's not just deal with equations. We can convert it to common sense. Open question, guys. So the cars that you drive, the gearbox that it has, suppose you just turn on the engine and you want to take off. the crank must deliver the torque to one of the gears. Would it transfer the load to the biggest gear or to the smallest gear? Raise your guess.
The biggest gear.
Why is that?
Because off the input shaft, it has the biggest reduction and yeah, gear reduction. So that will be spinning X amount, you put it on the gear, and it'll be spinning.
The answer that you said is correct. The reasoning I do not follow. Say it simpler. Why does it transfer to the biggest gear? Give a reason that everybody understands.
Because that's where you get the most torque out of it.
That's the reason. That's the reason. But when you want to take off, you want maximum power. You want to get off, right? You want to take off. So you need maximum power there. But when you're in highway, it's already having that momentum. You do not need torque there. You do not need power. It's already in motion. You just want that to speed up, right? You switch to the smallest gear. That's why you gear up. So you gear up and you get to the smallest gear. And why is that? It says it here. This inversely proportional, right? So that means the smaller the gear, the faster it moves. It's the two people are walking on campus. One is taller, one is shorter. The shorter person has to walk faster to catch up. That's the same thing. When it's already, guys, put the phones aside, please. When the car is already moving, let's say at high speed, you just care about speed. The torque is already there. So you can gear to the lowest, the smallest gear. So keep that in mind. I gave the point to you. All right. Having said these, we want to solve this problem. All right, let's solve this problem. And remember that if you want to have a copy of notes, I'm not sharing it. Instead, you're welcome to take a picture. If you want me to switch to any of the slides, let me know. What is it? Sorry.
What numbers?
The upper one is 240 millimeters, the lower one is 80 millimeters. So this example is from textbook with some simplification. Still, I'm able to convey the point of the problem to you with minimal computations. So we do this and then we get the break. All right, well, if I'm not mistaken, it's your turn, right? All right, no worries, I'll help you. All right, so the question is this, one at a time. So we see the two shafts are connected to each other through these gears, right? Different sizes. If these two are the same size, then the two torques on the two sides will be the same, right? If I apply this torque 900 on here, how much torque will you see on this gear or on this shaft? 900, very good. So 900, one at a time. So now the question is, if this is 900, what is the torque on the other shaft? And that's what we did in here. We said the torques are proportional or inversely proportional. Which one is it? Just look here, TB, RB. Proportional. So the bigger the radius, the bigger the torque. So this is bigger, right? Would you expect more torque on this or on this?
More on there.
On that. So then the dimensions are given. This is 240, 80. What's the ratio? What do you think? Just say the number, not the end number. Just say what over what?
Would it be 240 over 80?
3. Right? 3.
Oh, okay.
So what would be the torque on this then? If this is 900, the ratio is 3. So there should be,
1800?
you said 3.
Oh, 3.
Instead of 2 times 900, 3 times.
I'm confused, I'm sorry.
You multiply 2 by 900, multiply 3 by 900,
Oh, 2700.
2700. This is what you were doing in your mind, right?
Yeah, I was trying.
Okay. So then the torque in here, T, CD, is 3 times 900, 2700. So out of that little lecture, you need just this. All right, Olivia, point. All right, now Ray again. This is an inverse problem in the sense that normally we say, this is the object, I apply load to this, what happens? But in this case, it's opposite, because I do not say what the object is. I do not know the dimensions, but I say how it behaves if the material property is given to you. So this is an inverse problem. Normally, inverse problems are harder because we have to think backward, okay? So we did similar problem in torsion. When we want to come up with how thick an object should be when the material property is given, we did something. You remember that?
Yeah.
Look that up.
With the torques, we add and subtract.
Oh, I see what you're saying. I'm not talking about the load, the criteria. So you see what we did here for this one, for instance. You see there were 2 criteria. Let's say we only have material property given to us here. What was the condition? How we used that? Look at the equation there on the screen. First criteria, you see that?
Yeah, that's not exceed what
Yeah, this is the second one. Look at this one. And see how, try to follow this and see how we incorporated our U value. So whenever we say how thick it should be, that you're pushing the material to the strength limit. You see how we use this?
Yeah.
We equate tau max and tau u. We're pushing it to the strength limit. So let's do the same here. So tau u equals tau max. We have to do this for each one. So let's do it twice. This is for AB. This is for CD. So Reagan, please write it down. Whenever the question is how thick an object should be, say push the material to a strength limit. Keep that criteria, and whenever this question, the question is this, the approach is this. So when we say push it, we pushed it by saying how max should be at max this value. We're pushing it, right? This limit. All right. Then please give me the tau u value for AB.
Be the 50 megapascals.
Very good. And let's do it side by side. What's mega? 10 to?
6.
Very good. And what is tau u for CD?
Would it also be?
Also the same material. All right. Now, then on the right side, tau max is just equation, right? What's the shear stress equation due to torsion? We did it even today. We did it today too. What's the equation for shear stress due to torsion?
TR over J.
TR over J. So put TR over J. And then remind me please, what's the J for solid shaft?
Pi over 2 radius to the 4.
Fourth, it is. So AB, 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 and I repeat it also in here. CD or CD, pi half or CD to the fourth. All right, very good. So let's continue here. What's the torque AB that we found? Or AB? Yes. 900. So you see that eventually we want to solve for diameter AB. So I have to solve for RAB, and then what should I do to RAB to get to diameter AB? Well, I know radius. How can I get diameter out of radius?
Or is that
Radius, we want to get diameter.
multiple?
Multiply by 2. That's it. The point to you. That's the procedure for that stuff. All right. So RAB, I have, so one of them cancels out. So I leave RAB cubed in the denominator. And I do the same thing here. So we found 2700, and then pi halves remainder RCD cubed, because one of them cancels out. So solve this for RAB, solve this for RCD. For in millimeters. And then come to me, I'll give only 5 minutes. Whoever has done it within 5 minutes, I'll give them 2 points. So show both of them to me in millimeters. I'll do one of them for you here, the same procedure. RAB equals. What do we do? The same in the off diagonal, 900, pi halves, times 50 times 26. Cubic root of that. This is RAB. The same goes to our CD. Convert it to milli by dividing by milli.
Both CD and A.
Both. Yes, yes, please. Yeah, I asked you to come here so that I can look at it, and then if I see any issues, I can help you with that too. You follow this in
Yeah, I think there's some notes.
So it's the third root. Right?
Yeah, Q did.
Yeah, no, it should be third root, not cube. Square root is this, you see it? You see that? It's 1/3. You raise this quantity to 1/3. That would be cubic root. Yeah.
Oh, okay, just that.
Do that for both.
Okay.
So until 11:20, I'll look at that, and then we take a break until 11:30. If you're done, you're welcome to take the time and enjoy it. So 11:30, please come back by 11:30. This is 1/3. This is 1/3. This is third root. Guys, that's the third root. That means you raise it to the power of 1/3. Unit.
Yeah, those are still.
We'll see. Yes, just a second.
That should be high.
Oh, this is all in the numbers are. Oh, you have to divide it by 10.
All right.
Yes.
After Hawaii, I wonder how we can do that. First, we show me the set of patterns. What we have is show me that progression. It's an inverse level. It's in layers.
Yeah, so I saw
And then you raise it to power on.
Oh, I see. It's your
I mean, your power should be like some people might say, and might be absolutely hard, and the whole thing divided by the this is Gabe.
Yes.
if you want to share it with somebody, make sure that person learns it, teach it, not simply give him that, okay? Okay. All right, next to you. Great. Greece. Yep. You can do that. This is, you brought, oh, this is number 50 is in the denominator, and if you bring this to the maybe 6, but you brought 50 up, what happened to 50? Just check that. This is good. Where is this the first one? Which one? Is it just, this is off, this maybe you're missing one little thing.
Oh.
Yeah, hold on. Yeah, yes, only it's 2 months. Yes. Yeah, I'm sorry. 2 months. Oh, you found it out. Yeah, absolutely.
Was that supposed to happen?
Eventually, yes. Yes. I'm fine. I have to do something. My student said yes.
Bless you.
You did already, thank you so much. Millimeters, you have it here, that's packs, right? Yeah. Yeah, but you just, when you, if you do something like this in the test, you have hard time, there's a chance that you may lose points. I know. We're doing this to practice, so that basically other people, you have the maximum credit. Yeah. So along the way, you have to refine this. Yeah, to make it a little bit easier. Not for me, for you and everybody else. Right? Because if there's a mistake, how can you figure it out?
Yeah, I have a system that I've been doing this for most of my life. So my handwriting is very bad, so that's just how it's.
But yeah, I understand. Maybe one little thing. Maybe to pursue first of all. Maybe switch to pencil for a while. One thing.
The issue I have is like, and I can't even read whatever.
That's what. So use to preserve paper. Once you figure it out, you can put it to the needs way so that it's here. Okay.
Yeah, I want to have it on one.
No, I'm not saying here. Before you do this, just to have two side by side. Do something here and then put it. Oh, I see. That's what you have. That's it. Can you walk out of this? You go out of the country for now. See if you get the same. You figure out whether you. I see you taking care of you don't know this guy. Yes. Great. Great. That is yes.
I think so. I was doing,
This is correct? What was wrong there?
what I was doing was I took that value and then I put it back into this
Oh,
equation, and then that's the number I got, so
I
it
see.
makes sense.
Sorry about that. 2.3 numbers. Yes. I'm sorry, you want now, this is good for you. This is good for you.
Dude, that's the problem. I wasn't able to see it. So I literally just hit. There comes out to do way more than that. But jokingly, they have 75 visits. And then just like that. That's it. Yeah. So they said it right there.
It's which makes sense.
No, I only mean.
All right, guys. Any questions about torsions? Guys. All right. If no question, Professor Formova had told me that he didn't get the time to go over one of the important topics, but easy to handle, which is factor of safety. All right, we said normal stress, force over area, but it's all average value. When we pull or push on an object, it's not uniformly distributed on the cross section. Phones aside, please. Phones aside, please. Guys, phones aside, please. That's the policy. I want your attention. You put a lot of money to register for the course. You put in the time, especially cold. You come here, right? This hard weather situation. Let's get the most out of this. All right, so there is variability in the behavior and the cross section. Because of these effects or observations, when, let's say, even a company, single company makes an object, different samples would not be exactly the same. There's variability in material properties, and depending on how you load the object, one day it's loaded one way, the second day it's loaded differently. And then how it fades, what kind of failure type is considered, and then where that object is used. Do I use that object basically to write something? Do I use that object on an airplane, or a surgeon is using it for surgery? Really, the sensibility matters. Because of these things, we apply factor of safety. Yes, the response is not exactly uniform on the cross-section. We said we approximated with the average value. So we are overestimating for certain region, and we are underestimating that value for other regions. So which one is correct? We said we're talking about safety. As engineers, we tend to do the problem, solve the problem in the easiest way possible. Still the safest way. So instead of really developing big, long, let's say, complex equations, and then say the solution is this, which might be susceptible to errors or assumptions, we say we simplify it by making that assumption that the response is uniform, but we consider factor of safety. We say the answer seems to be this in average, but depending on the scenario, whether it's used in that, let's say on that airplane, or the surgeon is using it, or someone like me is using it for writing, we give it a factor of safety. It's a factor, it's a number, it's dimensionless. So this is dimensionless. Normal scenario, it would be 1. More sensitive scenarios, it would be more. All right. Now, these are the 2 equations that we would use, but with one common sense. So to understand that, I want you guys to help me. Guys, please pay attention. I want you guys to help me. Guys, please. I want you guys to help me. So suppose we take one of the elevators in the learning commons. And in the normal scenario, it says 20 people are allowed in at max. With a factor of safety of 5, how many people are allowed in? Raise your hand if you want to answer. I saw you first. What do you want to say?
4.
All right, next slide. 100, you said? 100. Also 100, and then anybody else? Guys, factor of safety, you want to make it safer, right? So you have to do division rather than multiply. At max, in the normal scenario, 20 people would be allowed in. In an earthquake situation, you allow 100 people in. You make it divide, right? If the factor of safety is 5, 20 divided by 5. Right? I don't know, what was the factor of safety that I said? 5. So 20 divided by 5. Who's it for? Anybody said? Or use it for?
No.
I'm sorry,
No, no, no.
28.
Braden?
Braden, yes. Point to you. So we do 4. So keep that in mind. You just simply divide it. The same thing is happening. Factor of safety was 5. Ultimate load in the normal scenario was 20. So applied load should be 4. Now, we can say the same thing about stresses because we have a linear relationship between them in this course. So, stress strain diagram. Our focus is on this linear region. Open question, guys. What did we call this linear region? Raise your hand. Yes? Elastic region versus plastic region. So our focus in elastic region, and for that region, this relationship applies. Now you want to solve this problem. If you haven't done it, please write it, and then, guys, please help me. Who's the next person to answer? I know Reagan did. Pax, you may have not done it, did you? Did I ask you a particular question? Then it's you. It's your turn. And then, of course, it may get down to several. Please get prepared. There's one little shortcut that we would do, and then we would account for factor of safety. I'll let you write it down, and then I'll teach you that. So before I forget, the test was scheduled for next Friday, but we're going to do the review next class on Tuesday. For Tuesday, bring your laptops with you, your tablets or a phone that you can connect with Blackboard. So we're going to do a lot of examples online together so that you get points directly on Blackboard. All right, so bring that. The description will be the same for everybody, but numbers will be different. So you guys can work together, including with me, and then you solve them, and then you get the points right there. Right.
Just as like a general rule of thumb, so for like stuff like elevators, for example,
Yeah.
they'll have higher factor of safety than, I don't know, a pop check in a car.
Yeah.
Like, because the safety factor, you want it to be higher, so when increased load, like earthquake happens, stuff doesn't fail. Does that go for a majority of systems where you have a safety factor? I think it's above 3. 3 is normally the normal safety factor for most things, right? And so does that apply to everything? Just assume it's normally 3, and then if it's something that people are in, you increase the safety factor along with that.
Right, so really that's subjective. Whether you take as 3, 2, or other numbers, really depends on the user. You can go really after any number. It's based on that person's discretion. But common sense is that normally people take it at least 2. And then the human risk is there, as the life risk is there, then it gets more and more. What number exactly is given? The textbook gives something, nobody would ever really look at the table that is the textbook is given. It's really subjective.
Okay.
Yes, Wasi?
What portion should be part of the test on next Friday?
Yeah, everything that covered would be part of that. So for your, again, we're gonna go over basic rubrics, we're gonna go over the policy and all the things that we covered next class. But you're welcome to prepare a good equation sheet. One side of A4. No worked out example, any equation, fine. Any procedure you write down, fine. but no worked out example.
Like note card or like an actual paper sheet?
I'm sorry?
Like a note card or a paper, like a full paper sheet, like an 8x11?
So anything that you have, it should be one side of it.
Okay,
Yeah.
okay.
Yes.
I can put like a method of how to solve something instead of like a work example.
No worked out example, you're welcome to put any equation, step 1, step 2 is fine, but no worked out example. I'll be looking at those equations. Your equation sheet basically. Yes.
Am I theoretically allowed to put a conversion chart for like
Yeah,
megapascals?
yeah.
Yeah.
So those, I specifically emphasize that, yes, put that table in there. Yes,
So just everything but examples we can put on there?
I'm sorry?
Everything but examples we can.
Everything but worked out example. All right, so Max, if you load this like that, you pull on it, what kind of stress do you expect?
Right? One that's perpendicular to.
That is correct, but what, do you remember the name?
So.
Normal stress, it is. So then, what is the equation for that?
I think it's a P over the area.
Yeah, I saw your hand, we call it sigma.
Okay.
If you tend to forget it like me, just put the name there, and then you spell it. Sigma equals force over area. We see that that applies to this, all right? So to emphasize that this is normal stress, we also have shear stress that we went over, or Professor Purnova had went over. I put this perpendicular sign there to convey that F and A are perpendicular. So that's normal or perpendicular stress. We said normal means stress in this scenario. All right, so we want to do this. Packs the points. I want to have enough question for everybody. Leo, right? All right. Leo, I asked Reagan something. The same goes to you. Really, this is sort of repeated pattern in this course. Eventually, you want to solve for diameter, how thick it should be. So, what's the criteria and what's the equation to start with?
Define diameter.
Mm-hmm.
Is it 2 over?
No. I'm saying, what's the criteria? What's the equation when we say we want to find how thick it is, or how thick it should be? I asked Reagan to write it. You remember that? You equate two things. You see that? Now I'm picking on you. But I said, please pay attention, please pay attention. It's like this. Reagan, please go for it. What is that?
The ultimate equals the max.
Very good. You push the material to its limit. So you equate the max values. So you say sigma U should be sigma max. Because max is all about normal stress. So the max normal stress that you observe versus the material can withstand should be equal. So sigma max is this. We equate this with sigma U. All right. Now, so Leo, so let's say if the factor of safety suppose is 1, normal scenario. If it's not given, that's 1. How much stress this object can tolerate? If factor of safety is 1, how much stress it can tolerate? Just read it, scale it there.
200?
Where are you getting 200? That's the force. Now, I'm helping her. By asking her question, I want her to understand. Yes. 500, right? Is this what you said? 600, yes. 600 at max, that's sigma u, the ultimate. At max, the 600 if the factor of safety is 1. If the factor of safety is 5, how much is it?
3,000?
What did we do here? It's like that elevator example. If factor of safety is 1, it's allowed up to 600. You want to be stricter there. You say more, you open it further, or you shrink it. So how much is that? Say what you do. Say what you do. What did you do? That's it. That's it. So from this point on, the shortcut is this. If you see factor of safety of other than 1, divide the strength value by that and cross out that factor of safety statement. Solve it without that. As easy as that. So here I point. So that's the shortcut, keep that in mind. So let's solve that. R3, what's the force that we have in this case? 200. Cross section is perpendicular area. What's the area of the circle? What's the equation for that? Pi r squared. We know that you can write it in terms of diameter like this, pi d squared over 4. Because I want to solve for diameter. So that's one way. So pi d squared over 4. I want to solve it, leave it there. So how much stress it can take now for factor of safety of 5? Could you remind us again? How much? So sigma u in this case is what?
Oh,
120, very good. So 120, mega is 10 to 6. All right. So diameter is 1.46 millimeters. All 3 points. Remember, the more the factor of safety, the thicker it should be, so that it can handle the load safer. So the only shortcut for factor of safety is you divide the ultimate value by the factor of safety. Everything else remains as before. All right, any question for me on factor of safety? Yes.
How'd you get to the 1.46? Did you just get d squared by itself?
So you're asking me that question again, then so let me do that here. If I have everybody's attention, if you learn it this way, it's just easiest really. This pattern, as I said many times, will be recurring in this course. Suppose I want to solve for D, what do? I want to solve for D. So put the fraction line, multiply 2 things and put them in the numerator. We want to solve for D, put these 2, B, C in the numerator. Whatever remains on the same diagonal as D, put it in the denominator. Well, it's the same approach if I want to solve for B. With the fraction line, B, what is off diagonal to B is AD, put them there. Whatever remains on the same diagonal as B, C, put it there. The same approach. I want to solve for B, solve C. The same thing. with the fraction line. Whatever is off diagonal to C will be AD. Whatever remains on the same diagonal as C will be there. The same approach. I want to solve for this. I would say D squared, solve for that first. So if it's not given, it's 1. So whatever is on the off diagonal to D squared will be these two numbers. Multiply 201. Whatever remains on the same diagonal as D squared will be these numbers. So pi fourth, 120 times 10 to 6. Josiah. Now if D squared is this, D will be square root of that. Okay, so this is how I would do that.
Thank you.
You're welcome. And of course, I'm converting it to milli and dividing by 10 to the negative 3. First, that's not done.
That was gonna be my question, is how do you determine whether or not it would be millimeters in this example, so as opposed to centimeters or meters?
I understand. In tests, I'll always be specific. I'll say, find it in millimeters, find it in centimeters. But here, I'm just giving you one representation. Yeah, I could give this to you in meters. So when I do not define it, anything you give, you define the unit, that's fine.
Okay.
But in test, I'll be specific.
All right, thank you.
Yes.
Is there any cases where the factor of safety be less than 1?
Who can respond to that? Can you come up with a scenario? Yes.
You can't have that occur because if the applied load is greater than the maximum load, then the structure will break.
Yes. So, yes, if you want to cause destruction, if you have a neighbor that you do not like him, consider factor of safety of less than 1, so that the cause break it. So Drew will want to. Did he answer your question?
Yeah.
Okay. So factor of safety is at least 1. It goes up at least 1. All right, any other question on this? So I want to use the remaining time to show you one more example. Maybe on shears. Maybe this example. When I was teaching, I came up with this example that I was able to put different aspects on it. So let's do this one. I want you guys to really understand these different stresses. I don't want you to get confused by different stress types. So make sure you do finish your homework. If you have any questions, you're welcome to stay and ask me after the class. If you send me email over the weekend, I cannot really respond to that, or late afternoon today. So do that as soon as possible. Get the points there. As an emphasis, if you get all the 4 numerical values correct, you do not have to submit any work. You do that only when you want to get partial credit for one of the problems, provided that you already got the other 3 correct. I think this is a really good example. I found it to be a really good example because it showcases different stress types that could occur, and we've gone over. So, reporting, right? I gave this idea last time. Yes, we do see two forces, but one of them is really reaction force. If I constrain it like this and I hide that force, it will be the same problem. I'm just exhibiting that force by saying that that's in equilibrium, that's the reaction force. All right, still no change. If I apply this force, remember that this component, this plate are subject to normal stress. So sigma equals force over area, but it could perpendicular sign there. Convey that force over perpendicular area. That means the cross section should be taken into account. Normal stress. All right. But as I pull on this, the pin, look at these two cross sections that are in contact with the plates, might get broken. As a result of that, on the pin, I have shear stress. Now, I think next is you after Audrey. What's your name? Yes.
Greg.
Greg?
Greg, Jerry White.
Great. Remind me the shear stress equation. Next is you. And Gabe, you also be prepared for some aspect of it. Yes, great.
Shear stress is V over A.
Very good. So what I do, I simply call it F over A again. But the area this time is parallel. So look at the force, look at these two cross sections, the circle are parallel to each other. So you see the same equation again, force over area. All right, so not only on the pin shear stress occurs, but also on this surface, or even the lower one, that groove exists. Basically, on joints, shear stress is one of the dominant stresses. So that's why it's asking for shear stress on the pin and for instance top, but bonded surface. If I do not say the shear and I say what's the stress value on the pin or let's say on the bonded surface, you should be really looking for shear stress value, not this one. I hope this gave you a better picture. All right, with that said, we want to go have the shear stress on the pin. Again, we set the force over area parallel of the pin, and then also shear stress on the groove. Force, and this is our pin, groove, area parallel of the groove. All right, great. Now, there are two ways we can look at it. We can view these two surfaces, you see the cross sections of the pin, being pulled by this plate and calculate the shear stress on the two plates, on those two little areas. Or I can reason that either one fades, the whole thing fades, right? Then I can say, just look at one of them and the force that comes from one of the plates on the right side. Would that make sense? I'm saying, let me repeat it. I'm saying that this pin could fail in two ways. One way is that the force that comes from the left plate causes the failure on the two surfaces. All right?
Yeah.
The second criterion is this. I could say that either the top or bottom section is getting failed by the respective force from either the top or the bottom plate on the right. Does that make sense?
I think so.
It turns out both are equal. So let's see why. So if the force is 500 here, what do you think the force on this is?
The same.
The same. All right, let's put 500. Then what's the area, equation for area of the pin? Look at the cross section, circular.
Oh, the R squared,
Pi r squared, give me the radius, please.
formula.
Radius,
Oh, 2
2, milli is,
millimeters.
milli is 10,
Oh, your 10 is something, millimeter. Oh, -30.
then it's good. That means you need to put it in your equation sheet.
Yeah.
Okay, so -3. All right, so that's from the left, right? Let's analyze this. It turns out to be equal, so that's why I put the equal sign there already. But let's analyze just the right side and just analyze this top circle. What's the force? If this is 500, how much of it goes to the top plate? It's symmetric.
If you look at it like two parts, you say like 250.
250, that makes sense. And then, oh, we said by the way, we said two of them, right? I forgot to put the two there.
Yeah.
We said two areas. For the 500, I put it there. All right, now we said only one of the areas, right? So I put just one area there. Aren't these equal?
They should be.
500 divided by 2 is 250. So whether we say all the force went to both areas, or half of the force went to one of the areas, it's the same thing, right?
I'm wrong with that.
Yeah, that's basically the common sense behind it.
Yeah.
So that will give us the same value. So great point to you.
Appreciate it.
Appreciate you. So this is 19.89 megapascal. The textbook calls it V instead of force because it simply gives it an extra adjective. It says V is shear force, vertical force, shear force. We would still say force, the area is parallel. All right, okay, let's now work on blue. We're just looking at the top bonded surface here. So 1, 2, and then the glue here, okay? So if the force is 500, how much of it goes to the top plate? 250. And then give me the area of the glue on the top surface.
That's 60 millimeters.
Very good. Millimeters squared, isn't it?
Yeah.
Not millimeters. So 10 times 10 to negative 3 times 6 times 10 to negative 3. Make sure you put that 10 to negative 3 for each one of millis. All right, this is 4.17 megapascal with 0.2 gauge. Again, remember, we do all this calculation for a reason. We want to be able to comment on the mechanical safety of this object. Let's do a suppose question. Was it? Remind me, please, your name? Ethan. Ethan, suppose, I'll ask you one and then go to Nathan. Ethan, suppose, because it's all about shear, I have to give you shear strength this time, right? Even if I give you normal strength in tension, you should not be using it, right? So that the limit here should be tau u. Suppose tau u for pin is given as 30 megapascal. What would you say? Is the pin safe or not, and why?
No, because it isn't reaching safety, or the safety isn't visible.
So let me help you with this. You have a good car.
No.
It drives. No, suppose you have a good car, and then it drives this up to, let's say, 180 miles per hour. Okay.
Pushing about 80, but okay.
Right. You get the ticket after today. So suppose it can go up to 180. If you go with, let's say, 80 miles per hour, would you cause failure in car?
No.
So this is the same thing. So it says when it says U, that means that cap value, that max value, is 30. How much are you giving it at max?
No.
How much are you giving it at max?
How much are you giving it, or how much is it?
How much are you giving to the pin at max?
30, or 20, sorry.
Yeah, about 20, 19.89. So is it good or not now?
Yes.
All right, do simply like that. Say this is greater than 19.89, so it is safe. Pin is safe. Okay? So Ethan, now help me with this. I want you to get it now. So now let's talk about glue. So you go to Home Depot, for instance, Menards, you want to pick basic glue. Just look closely there, see what that shear stress max is given there. Make that decision based on that, not just basing the brand itself. Okay? The bigger it is, the better it is.
Right.
So suppose tau u for the glue is, let's say, 1 megapascal. So what would you say?
The glue is safe.
You really do not have a good car. But I'm joking. Do the same procedure. What should you be comparing? With what?
It's not safe because the megapascals are higher. Or
Which- yes.
4.7 is higher.
Very good. So this is less than 4.17. Ethan, this is really the subject of this course. You're gonna, you and everybody else will be asked this question over and over in the test. If you get it wrong, you will not get the point. So please remember that. So this is not safe. So overall, would you say this is a good design or not? One failure, too many. So not safe. All right. Ethan, your family name please starts with?
Jackson.
Jackson. I did say Jack, so I think I got some portion of it correct. I was thinking of that. All right, point to you. Very good. So please come prepared next class with some electronics so that we do everything on Blackboard. Make sure you finish up the homework it's due on midnight on Sunday. And enjoy your weekend, guys.